So far in this unit, we've been talking about one-dimensional measurements of circles, such as measuring the outside of the circle, that's called circumference. We can measure how far it is from one end to the other, that's diameter, or we can measure the center to the outside of the circle, that's radius. And in this lesson, we're going to start thinking about the areas of circles, which is a two-dimensional measurement. How can we measure the space inside of a circle? So for the warm-up, we're going to consider the space inside of some different polygons. Polygons is a fancy word for shapes that are closed and don't have circular sides. So A and C are polygons. B is not a polygon. But look at the space inside of these two polygons and the circle. So think about, which figure has the largest area? Let's call these figures, because not all of them are polygons. Two of them are polygons. The green one is not a polygon. Which figure has the largest area? Pause the video and think about which figure has the largest area. So these are without a grid, and this might be easier to think about with a grid. Try to do without the grid, and then at this point of the video, you can look at them with a grid. And with a grid, it's a little bit easier to think about which figure has a larger area. Is it the two polygons, or is it the circle, the figure that is not a polygon? And you might decide to count the squares, or you might think back to 6th grade and think, so how might you calculate the area of these, or think about the area? So for A, figure A, you can, that's a rectangle, so you can do length times width. So figure A has a length of 6 units, and a height of 5 units. And that area is 30 units squared. An area is always going to be in second dimension, so that's squared. That 2 is telling us that's in the second dimension, units squared. So 30 units squared. How about C? Well, C, recall from 6th grade, C is a parallelogram. That is a parallelogram, and a parallelogram is also base times height. And the base and height are perpendicular. Base and height are perpendicular. So our height is 4, and our base is 1, 2, 3, 4, 5, 6. Our base, 6. That is an area of 24 units squared. But what about the circle? The circle, we can't really use base times height because it's not a polygon. It has curved sides. It doesn't have straight sides. So what's the area of that rectangle? That rectangle is 4. 1, 2, 3, 4, 5, 6. That's 4 by 6. That's 24 units squared. Now, 24 units squared is the same area as the parallelogram. So we know this circle is more than that rectangle. So that circle is a greater area than the parallelogram. So that parallelogram does not have the greatest area. But what about the rectangle? So what has a greater area, the rectangle or the circle? Oh, we also know that there's a couple more rectangles in here. So that rectangle, the area is 4. And this rectangle, the area is 4. That 6 is a little confusing, so I'll erase that 6. It's an area of 4. And so it's 24 square units for this rectangle. And then it's another 8 for those smaller rectangles. So we do know it's larger than 30. And so this circle has the largest area here. So now the question is, what is the area of the circle exactly? And that's what this lesson was going to be about. In activity 7.2, we're going to be estimating the area of circles. And this is going to be similar to a few lessons ago. We estimated the circumference of circles and graphed it according to circumference against diameter. This time we're going to be graphing area against diameter. So here's our table, estimated area and diameter. And for the estimated area, you're just going to estimate the area, just like we did in the warm-up. You're going to try to make, shapes within the circle. I'm going to show you how to do that. But first, cut out your circles. You'll need to find the area, estimated area and diameter of two different circles in order to get a line on your graph. So cut out your circles and measure the estimated area and diameter. And I'm going to show you how to do the estimated area. So let's say this is your circle. Okay, so we have a circle here. And diameter you measure across the circle. So you would go from one end of the circle, say right there, and then all the way right here, all the way to the other end of the circle. And you need to make sure it's exactly across the circle. You can draw a line anywhere, you can draw a diameter anywhere in the circle, but it's best to make it someplace easy where you can easily measure the diameter. So now we could just count. Sometimes you can measure it with a ruler. This time they give us a grid, so you can count the units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the diameter is 16. So we're going to come back to our table. Go back to your table. So now we're at our table, and you write 16 for 16. I'm gonna use units, assuming that each square is a centimeter, so 16, diameter is 16, and then let's go back and find the area, estimated area. So we're gonna do for the estimated area is we're going to draw a square around the circle. Approximately, just estimate, but let's see, we can go right here. So let's draw a rectangle right there. This is just an estimation, it's not exact, because there's squares outside and inside that we're missing. But you might say this is this rectangle is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 across, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so 14 and 13 times 14 is estimation area. So if we do 13 times 14, it's 12. 40, 30, and 100. So the approximation for the area is about 182. Now we missed a few, I would say we missed more rectangles than we added, so maybe we can say approximation is 190. And it's just an estimate. Now if we go back to our table and write the area as 190, okay, so now we need to do that with one more circle, and the good news is the second circle is a little bit smaller. Let's go back to our second circle, and you might have this circle, you might have a different one, but we got a really small one. Okay, so we can estimate the area of that to be about 4, maybe a little bit less than 4, maybe 3.5, because that is a square, that area with 4, and it's less than that. So maybe 3, we can say it's 3.5. It's just an estimate. And the diameter would be 2. So 2. So let's add those to our table. So diameter is 2, estimate area is 3.5. Okay, so now let's come down to our graph. Okay, next you're going to graph that. So you're going to graph. Let's graph those numbers. So the smaller area, the smaller circle had a diameter of 2, and then an area of 3.5. That's way down here, way down there. And that is definitely not exact, but I can't zoom in with my Apple Pen. But it's just an approximation. And now let's graph the larger one. So the larger one, 16,190. 16,190. So it's 16, diameter is 16, and then 190. 190 is up like there. Okay, so the line is gonna look something. It's really difficult to scale. Let's do another smaller circle. Let's do a circle that's it's smaller. It's smaller than the larger one, but it's a little bigger than the one we did. So let's do this one. Okay, so the diameter on this is, there's the diameter, 1, 2, 3, 4, 5, 6. And the area, let's just draw this rectangle right here, which might be a square. Okay. 1, 2, 3, 4, 5, 6. It's 6 by 6. You actually know it's 6 by 6 because it's the diameter. The width is diameter. It's 6 by 6. So area is 36, but you subtract 1, 2, 3, 4. Let's just subtract 5. So let's say 31. So 6 and 31. Let's go back to our table. 6 and 31. I think that's going to be a little bit easier to graph. So if you do have a smaller circle, maybe collaborate with a partner who has a circle that's a little bigger. But if you do 6 and 31, it's approximately right there. Now that I have these 2 points, I'm actually going to put that first point that was really hard to graph back in our graph to 3.5. So I'm going to try my best here. 3.5 will be somewhere like right there. And if you try to graph this, you will notice that this is not a straight line. This is not going to make a straight line. This line is going to, in fact, increase and curve at a faster rate. So it might look something like this. And we learned about proportional relationships. Let's zoom in that a little bit. We learned about proportional relationships, and that is not a proportional relationship. One of those quantities is increasing at a faster rate than the other one. This is not a proportional relationship. Now, think about which quantity looks like it's increasing faster than the other one. And that would be the area. The area is increasing at a faster rate than the diameter, which means, again, this is not a proportional relationship. If we scroll down, so here's the graph for diameter and circumference. And look at our graph for diameter and circumference. And that is a proportional relationship. That is a proportional relationship. And let's go back. We can scroll down a little bit more. This is the applet. It's very clunky, so I didn't use it. Let's scroll down to a table. So here's a table with diameter, area, and then there's area over diameter. area over diameter. Just like when we talked about proportional relationships, if you put x over y is a proportion. It's a proportion, so that will always be the same thing. It will always be, let's call it z. You can call it anything, but let's call it z. So x and y will always be z, no matter what you can go down to any row, and diameter over estimated area, area over estimated diameter should be the same thing. But if you notice, it's not. So this here it's 1.5, here it's 2.3, 3.0, and it just increases. Estimated, the area is over the diameter, so as it's increasing, that means area is increasing at a faster rate. Here you can see some more increasing rates. Here's what I mean by area over diameter. Area over diameter is increasing. That means area, this number, area, is increasing at a faster rate. That brings us to the area of a circle. And the area of a circle is calculated by the radius, which also has to do with diameter. So usually they use radius. In trigonometry, they definitely use radius way more than diameter. Just there's more you can do with radius, so they use radius. But radius is half the diameter, so if you know the diameter, you can get the radius. But anyway, if an area of a circle, so if the radius of a circle is r units, so the radius is r, radius r equals radius, r equals radius, then the area of the circle is pi r squared units. So then area pi r squared. And if you notice that that is a squared unit of measurement, that's in the second dimension, pi r squared. For example, if a circle has a radius 3 inches, its area is pi 3 squared square inches, or 9 pi square inches, which is approximately 28.3 square inches. So again, so just like circumference, you can actually write area equals 9 pi inches squared. You don't have to calculate it out 28.3 square inches. You could write 9 pi inches squared. What's important to note is that you should have this, squared. Needs to have the square. Here is the lesson synthesis. And this is the main idea for this lesson. If the radius of a circle is r units, then the area of the circle is pi r squared. Area of a circle. So how do you get the area of a circle? You need to know the radius, and then you would square that radius and multiply it by pi. Try the cool down. Circle A has a diameter of about 20 inches and an area of 300 inches squared. Circle B has a diameter of approximately 60 inches. Which of these could be the area of circle B? Explain your reasoning. Pause the video and try this problem yourself. You actually don't need the information about circle A. And it's there, I think, in case you forgot how to calculate the area of a circle. You could find the relationship between the diameter and the radius. But you actually do not need the information about circle A, because you know that the area equals pi r squared. And in this case, the radius is half the diameter. The diameter is 60 inches, so the radius is 30 inches. And area is pi times 30 inches squared. And we can approximate that to pi times 900. And usually the number is written before the constant, so 900 pi. So 900 pi. So we know it's not 100, it's not 1, it's not 2 or 3, it's not 100, 300, 900. It's got to be the 2700. And 900 multiplied by 3.14 is approximately 2700. So the answer would be 4.